Alright, hello. This is Junichiro Horikawa. Can you hear me? Okay, so this is 10 p.m. on Saturday. I would like to start this week's tutorial live for Houdini, which is called as Houdini Algorithmic Live. And this is the 79th episode. And the topic for today is to create a video stippling effect, meaning creating an image stippling from a video frames using a technique explained in a paper called 2.5D Computational Image Stippling by Kin-Ming Wong and Tien-Tsin Wong. Okay, so today I'm just going to try to implement what it shows in this paper and see if it's going to work in Houdini. Right? Now, one thing to notice, I am not going to fully implement the function explained in the paper, since it is the process explained in the paper is assuming that people are going to use a GPU to calculate. Although I am not going to use a GPU, or I'm not going to write any GPU code inside Houdini nor OpenCL, I'm just going to use a Vex in order to achieve the similar effect. So I am going to deform some of the function so that it can somehow be used in a rather real time than rather wait for several minutes to finish calculating. Since Vex is, I think its Vex is on based on CPU, so I'm gonna try to strip down some of the functions explained in the paper to make it a bit more faster. So the actual result might not be the same as what it explained in the paper, but at least from my point of view, it still shows a good image. So that's just that. At least you will understand what I'm gonna try to do here. So if you know how you can code in GPU, then I think you can just transfer back into a different language for sure, once you know the underneath algorithm. Right, so what's so special about this algorithm explained by these two guys for computational image stippling? Now this is another example how you can convert the image into a blue noise, which is this kind of scattered point. And as it is explained in the paper, there are already many examples to achieve the same pattern. But what's special about this method is that it's using a physical-based simulation for sampling, using a point charged method. So because of that, you're going to implement some physical simulations per point, and because of that, if you use it for moving frames, and if you apply this simulations on each frame, time by time, frame by frame, you'll be able to create an effect such that the point seems like it's moving toward the next frame's image. And so you can kind of move the point at each frame to mimic the underneath image, rather than compared to the other stippling functions. If you use the other stippling functions, if you try to do it for videos, each frames you get a random point position, so you don't really get this smooth transactions of these points. But because this method is based on the physical based simulations, you get this smooth interpolation of these points. So I think that's what's interesting about this method. All right, so that's what I'm going to try to achieve here, feeding the video images, the image sequence extracted from a video, then converted into a stippling image and play it like this. That's our goal here, by trying to implement what it shows in this paper from scratch. Okay, so that's that for the basic information. Let's look at the paper. Where should we start? So looking though those paper, this paper shows three different steps in order to achieve the final image. And one thing you need is the base image, obviously, and it is also, oops, what had happened? It also asks you to provide this depth image as well for additional effect. But what I'm gonna do is just to use this original image, and I'm going to skip using this depth image. So in this case, the section that I'm going to focus today from this paper is just this section 2, a physically based blue noise sampling. The section 3 is explaining how you use the depth image to create a focusing effect based on those height field informations. I guess it's not that hard to do. You just need to update the distance function or the charge functions right here, instead of the one explained in the section 2 right here. Though I am going to skip this, and I'm just going to try to implement the base physics based blue noise sampling technique explained in section 2. And once you be able to do that, I think you'll just understand how you can do the 2.5D images as well later. All right, so focusing on section 2, I know that I need to provide an image, and let's see what else I need to provide in order to start doing it. Now it is explaining that I do need so each particle, it explains that each particle has a charge informations, and you have two forces applied on each point. One is the positive charge, which is going to be used to create this uniform sampling, so that the point has the similar distance to each other, like these. So by using a uniform positive charge, you'll be able to create this kind of image first. So this is the first goal to achieve, creating this uniform point set. And after that, you would need to create this adaptive sampling by providing an image. And by using an image, you're going to create a additional plane. I guess it's better to explain in the sketch, I guess. Alright, so let's see. So there's 2 steps involved in this algorithm. Step 1, first of all, you create a image plane. In this case, I'm going to make it simple, as inside the paper I'm going to make the plane size equal to 1 for width and height, to make it simple, starting from 0, 0 and 1, 1. Okay, and basically I'm going to start by scattering the random points on top of the plane randomly, maybe using a scatter node in Houdini. And maybe without relaxation option, so that we can see how it relaxes, how it uniformly relaxes using our functions for step 1. After you have created this plane with the scattered points on top of the image, what we're going to do is to apply a charges to each of the point using this function right here. So at each point you have an f value. Okay. And this f value is being calculated by looking at each of the point. From this point, you're going to look at each of the point, like comparing with this point, comparing this point, comparing this point, comparing this point, and so on. Taking the distance and the direction, and using those information, you can calculate this fi. And you do the same things for all the points. So you can imagine that the calculation cost is, if you have a number of points like n, then the calculation cost is power 2 of n. Now that's a lot if you want to do this in real time. Now that's the reason why it suggests you to use a GPU for fast simulations, though I'm not gonna use any GPUs or OpenCL here. So what I'm gonna do is to try to reduce the number of points look from this each point by setting up the radius, the search radius, okay, or the maximum point numbers from this the center point. Now by doing that, the sum of the information being lost, especially if you look from this point, then all those points right there, it's going to be ignored. But if you look at the paper, you can see right here, the smaller the distance is between the points, this is the distance information, this is the distance between one of the point to another point. Okay, so and this is the distance square of the distance. So if the distance is smaller, then these values become bigger, but if the distance is big enough, then this value is going to be really small. So I kind of assume that if the distance is somewhat big enough, then this value might be able to ignore it. So that's what I'm going to do here in order to make the simulations a bit faster in terms of using a CPU, because I'm just going to use vex here. So that's what I'm going to do. And Eji is the directional vector value from point J to point I. In this case, if this is the point I and if this is the point J, then Ji is this direction. Okay, so that's that, and you'll be able to, by calculating the fi, you'll be able to get a vector value. So this fi is going to be a vector value. And use it as a force. Now this itself cannot be added to a point position to move, but you need to create the actual force vector value in order to move the point, and that is based on the Verlet physics, and which is explained somewhere around here, which is this one. So we're going to use this customized velocity Verlet numerical integrator in order to create the force vector value, and then we can move those points based on those forces to a specific direction for a convergence, and as a result you'll be able to sample, you'll be able to create the blue noise sampling. Okay. So let's try that out. And the equations for this Berlet integrator is being explained right here. So this is what we need to implement. And since this is the recursive functions we can obviously use solver for this functions. It's not that easy. It's not that hard to implement, I think. By looking at these functions, it's pretty easy to understand. First, you need to update the position based on the velocity and the acceleration value. This is the velocity. This is the acceleration value. And D is the maximum displacement value that you can move in one frame, one sub-step. And then next you're going to calculate the acceleration value, A, by using the updated positions, which is this one right here. And next you can update the velocity using the same displacement value together with this S, what was S? The dumping value to slow down the velocity, and together with the acceleration value, the current acceleration value, and the previous acceleration value and the current acceleration value. This is the acceleration value updated right here. This is the acceleration value which was previously used before updating the acceleration. So you have two types of acceleration value. Now that's what you need to do in order to update the force information and change the positions, and as a result you should be able to get this uniform sampling image. So that's our first goal to create. Now after that we can come back to create a second, we can come back to do the second step, which is to use the image that we're going to provide to adapt to create a image, something like this, image based blue noise sampling. Okay, so what we're going to do in this second step is to provide a image which could be underneath or above the original scattered point plane. Okay, and the image is going to be explained as a grid of points. So you're going to create a grid out of the image, and at each point on the grid you have this color information, or if you're using the black and white image, you have this intensity value for each pixels, and you use this intensity to create another force, another charge information, and this time you're going to create a negative charged information. Okay, and the rule here is that the total positive charge from step 1, let's say that's F total, and let's say this is G total, and when you add those two values, F total plus G total, in terms of the absolute value, or not the absolute value, but the value itself, you should get 0. So this one is negatively charged value, and this is the positively charged value. So the rule here is that F and G, when you add those two forces to get two charges together, the value should be 0. And that's the rule here. And as I said, if you pick up a few points out of these search radians, then what you need to do is to calculate the total amount of positive charge within this range, and same for this negative charge as well. If you are using this point as a search radius, within this search radius you pick up those pixel information from the image underneath, and you add up all those negative charge informations coming from the intensity, and those additions, like let's say F part and G part, those addition also has to be 0. And in order to make the total amount of the force or charge to be 0, you need to kind of calculate the coefficient value, which is called as A in the paper right here. Okay, so that's what you're gonna do, and this is how you calculate the negative charge information based on the intensity, and this is the intensity right here. Okay, so if you do these calculations, you'll be able to get some vector values, and as a result you'll be able to calculate, or you'll be able to update the point position to where it converges, and as a result you should be able to get the image something like these based on the intensity of the image. So let's do this. All right. Sounds a bit hard to implement, but if you do it from scratch one by one, I think it should be able to, it shouldn't be that hard to implement. It's just that if you want to use the GPU instead of CPU, then that's not my field, so maybe you can do it by yourself and maybe show me how you can do that. Okay, so I'm gonna use the geometry. I've just created the geometry node, and let's try to find out the image that I'm gonna use first of all. So let's go to the website, look for the image that you want to use. I mean, you can just use anything, I think, but the image with the high contrast in terms of the grayscale might be a good idea to use. So let's find out that kind of image. So I'm gonna use the Envato elements since I have subscribed in this one. Let's search for a cat or something. Okay, so let's say I'd like to use this one, kitty. Let's download this one. Right, and any format is fine, I think. Just download any image that you want to use. I'm gonna start by testing with the still image, then later on I'm gonna try to use it with the video frames and see if it's still gonna work. Okay, so let's do this. I am going to just drag and drop the image that I've downloaded. Okay, looks like this. Kind of a squarish image, so that's also good. Right. So first thing first, let's import that image. And to do that, I'm going to use the attribute from map node. And in order to use this, you kind of need to have a grid before importing the image. So let's create a grid, and let's have enough point to show a crisp image. So I'm not sure how many points I need. Let's say 512 by 512. And the size of the grid is going to be 1 by 1 for ease of use. I mean, it actually can be any values, but based on the paper, I would like to use the same parameter values, so I'm gonna keep the size to 1 and 1. And also I'm gonna shift the grid so that it will align from 0, 0 to 1, 1 in terms of the XZ plane. So I'm gonna shift this center by 0.5 and 0.5. Oops. Is that correct? Yeah. Like this. Okay. Now let's look at how many points that I have. So you have 262,000 points. I guess that's enough. So let's try to import the image. Let me first save this so that I don't lose the information. Where is it? Okay, I'm going to call this video stippling. Alright, now let's import the cat image like this. Now it's kind of flipped, so let's do a UV flipping invert V. Yeah, that should be fine. All right. And yeah, tons of information. And let's first retrieve the intensity value from this image. Currently I have R, G, and B information applied as a color attribute. Like this. Now let's convert this into an intensity, and in this case the intensity could be a lightness. And in terms of lightness, I think I can just first convert the LGV value to HSV and then just get the V value, the value. So let's try to do that. Let's also hide the grid. Alright, so I'm going to get the intensity. First thing first, I am going to get the color value and convert it into HSV by using a function called RGB to HSV, converting the color vector value. Now if you just get the Z value for the HSV, I think you get the intensity. Now you just have converted the color image into a grayscale image, and this grayscale value is going to be used as the intensity. Okay. Now that I realize that now that I have prepared the image for the sampling, let's go back to the step 1 and try to implement the base uniform sampling using this FI, using the positive charge information. The charge information itself is the one called QS right here, and this is actually the positive value that we need to create, and it shows different image result by using a different value. Looks like if you use a higher positive value, you get more high contrast image rather than using the smaller value right here. Okay, so let's see if that is so. Okay, so looking at this equations right here, it's pretty easy to implement. The I means the current point number. The j is the one that you are looking from this point, and I is not equal to j. So obviously for that we could use a point wrangle first of all, and in this case if you use a point wrangle, then I will become ptnum. So at each for each point we're looking at each point to do a process using this point wrangle using a bex, and in this case I becomes ptnum. Now for a j, in order to access all the other points inside from the scattered point, and I kind of see that I don't really have a scattered point yet, so let's also create that. So let's create a randomly scattered points by not using any image information but from the original plane, and let's not relax the point but just randomly scatter the point on top of a plane. And obviously you can set the number of points, how many points you want to use here. Let's try with 10,000 points. Okay, now I think it also is a good idea to have a null node to have all the parameters that we want to control later. So let's have that as well. Let's create an integer value to determine the point number. Point yum from 0 to, I don't know, 100,000. Alright, then for now let's make this 10,000. Let's link the parameter value here. Now if we look at the points, it's a bit hard to see what's going on with this background, so let's make the background white by creating another grid which covers this plane right here. So maybe I can just scale the original plane with some scale information. Let's try to transform the original plane maybe by 2 and merge it together with the point, so that if the grid is white, then we'll be able to see a point a bit more clearly. Now let's also set the pivot for the transform to be the center of the plane. Like that, and let's also look from the top view. And currently the plane is a bit grayish, so let's go to the background or the material and let's make the diffuse to white. Okay, so it's a bit more easier to see what's going on. Okay, maybe I can make the grid a bit bigger. 5. Alright, looks good. So this looks like a good setup in order to visualize the point. If you want to scale up the point radius, you can go to the geometry. By pressing the D key, you'll be able to get the display options. You can change this point radius. Maybe depending on the number of points, you can reduce the radius or increase the radius pixel. Alright, now let's bring the point wrangle after the scatter. Then let's try to calculate a positive F value, the force value here, using the charge QS. Okay, so if let's see, the QS is the amount of charge carried by each particle, and this is the parameter that you can choose by yourself. I is the number of points and j is the other point number, so which is determined by the number of scattered point. N is the number of points you have in the space. Eji is the directional vector from j to I. So that's pretty straightforward. Let's try to get that. So let's first get the QS value, determine the QS value by yourself, which is the float value, probably from 0 to 1, I think. Okay, and in the example it shows something like 0.05 or 0.35. Maybe let's try with the 0.3 or something. Alright, so 0.3. And I think this QS can also be parameterized and being used as a global value here. So let's do that. Going to drag and drop what I have created right here to right here as QS. Positive charged value for the uniform sampling. Alright. Now, based on this value, let's try to calculate this one. So, first thing first, as I said, if you are trying to look at each point, if you try to search for each point like brutally, it's going to be pretty slow in order to calculate, because for each point you have to look for other 100,000 or 10,000 points. So that's the reason why I want to reduce the number of points to look for by maybe using a function like near points. But just for testing, I'm going to try to just look for all the points as an initial test for to see what the implementation is supposed to look like. So the number of points we're looking at is the points, and for each loop the I is going to be the point number for the target point, which in this case j, so maybe we better call this j instead of I. Okay, now and might be easier to understand if we say I is equal to pt num, so it corresponds with the paper value right here. Okay, so and we do have a conditions I is not equal to j, so let's give this condition. If I is not equal to j, then that's where we can calculate this fi, or this value here. And this is the integrator here, and integral here. We can add up or calculate the mass addition of this sum of these equations for each for each j value. And if we look at this one, and after we have after we have made the sum of these functions, we can then multiply by the square of qs, which is a positive charge value. So let's try to calculate what's in here, what's inside the loop. So that is, first of all, we have this vector value going from, which is the uniform or unit vector value going from rj to ri. So in order to calculate this, we need to have the point position for j and I. So let's get that. The position I is obviously a at p. Position j is a point information at j. Alright, and the EJI is a direction going from position j to position I, so you calculate the subtraction between position I and position j. And since this is a unit vector, we need to normalize this, right? And then after we have calculated this unit vector, we are going to divide it by this distance between the Ri and Rj, the square distance between the Ri and Rj. So for that, we could use a length 2 function between the Ri and Rj. We can just say position I minus position j for that. Okay. Now that we have calculated this value right here as a vector value, we're going to add up until we leave the loop. So let's make a value called fi outside the loop, starting from 0, 0, 0 as a vector value. And then at each loop iterations, we're going to add this eji and as a result, you'll be able to calculate this part right here with and the result is fi, called fi. Now finally you can multiply with this, the square of qs, so fi multiply by square, or qs multiplied by qs. Okay, and that's that. Now that I have calculated this fi, we can now store it inside a point as an attribute. Let's just call this fi something. Fi is equal to fi, right? If we look at this one, we now have this value right here, which can be used to convert it into a force value to move the point to separate the points uniformly, creating a blue noise sampling. Okay, so the next step is to use this fi value that we have created together with the valid integrator, which is explained right here, numerical integrator right here. Okay, so let's do this. And wait, where'd it go? Right. So, and since we have to update this at each frame, we're gonna do this on solver. And because we're going to use this in solver, the calculation that what we have just done right here must also be done inside a solver as well. Okay, because each frame the point position changes, so obviously the fi value also changes. So we need to also calculate this inside a solver as well at each frame. So let's create a solver and connect the scattered point, and reconnect to a solver like this. And let's cut and paste what we have wrote right here. And how do I name this? I don't know. Charge. I don't know. Stippling. Okay. Now the path has changed, so let me update. Guess one more. Right. So now I have the correct QS value, and I have also calculated the Fi value. It's time to calculate the actual force value in order to move the point to a specific direction. Okay, so let's go back to the paper again. Maybe show this part, the numerical integrator part, and see how it should be done. So first of all, we need to update the position, then update the acceleration, and then update the velocity. Now the information we have is Fi, and Fi is actually is based on is the information for the acceleration value actually. So which is this part right here. Okay, so we are going to first of all, I'm going to separate those functions with different wrangles for ease of visibility. So first of all, I'm going to create this position update node maybe beforehand. Like this. And then for the acceleration update, I think we can just do it inside the stippling, and also the velocity update can also be done in the same wrangle. So let's do it like this, and let's try to do the stippling part first, right here. So I do have this Fi value created as a force, and the next thing I like to do is to actually try to use this with this equations. Let's see where it should go. Right now, actually, this this Fi is based on the current point position right here. Okay, so if we look at this, this is actually computed from an x at t plus delta t. This is the updated point position actually, which is explained right here. So in the first step, position update, we are updating the point position. In Houdini, we're calling this at p, using the previous point position, and together with some velocity and acceleration value. Then we have updated. Then we're going to use the updated point position, which is this one, in this case this one, to create the acceleration value. In this case, this is called Fi. Okay, so we can actually say vector ACC or new ACC is called as Fi. Right? And so we're done with this one actually. We're done with the second step. So the next, what we need to do is the next step part where we're going to update the current velocity value using the previous acceleration, which is not this one, but the acceleration value calculated previously. So because of that, you need to have this information maybe inside the attribute as a previous acceleration value. So let's say let's create some attribute that we're going to need. And I'm going to use the attribute create, and all of them should be vector value in terms of velocity and the acceleration. So first of all, let's say the current acceleration value is called ACC, which is applied for each point and which is also a vector value. Okay, And let's create another one, which is called as velocity, which is also a point class and a vector value. Now I probably don't really need the previous acceleration attributes because I can just get it. I can just deal with the current ACC value here. So let's just have those two attributes, velocity and acceleration, and I guess that's all we need here. Right. So going back, let's check. Look at the geometry spreadsheet and make sure you have two attributes, ACC and velocity, right? Then going back to the stippling point function, for maybe I'm going to create a comment. Calculate acceleration. Okay, now after that, calculate velocity. Alright, I might not need to have an FI attribute after all. So now I have this new ACC, and I know that the previous acceleration can be accessed by looking at the v at ACC attribute, and the previous velocity can be accessed by accessing to the v at velocity. So and the one that says t is the previous value, and the one that says t plus delta t is the new value, the next step's value. Now new ACC is this acceleration with t plus delta t, and the AT is the previous acceleration value, and the VT is the previous velocity value in this case. And we also have some conditions here, like the minimum. So the size of the whole vector value should be clamped with this value here, which is the distortion, the maximum distortion value, which is going to reduce how much the point should move in each frame. Okay, and it says in the paper that the best value for a uniform size, which in this case 1 by 1, the width equal to 1, height is equal to 1, the d value is works best in 0.002. And S is the damping value, and in this case 0.95 works best in this case, which is this one. So let's keep that in mind, and let's calculate this velocity here. First of all, let's calculate this part. So we need an S and D first. So S, let's give that as a parameter. S is the damping, and D is the maximum what was it called? How is it calling? Maximum displacement. So meaning how much what's the maximum value it can move, and the point can move. Alright, so let's keep those as a parameter, and in this case S is 0.95 and D is 0.0002, was it? 0.002, like this. Okay, now I think I have enough information to calculate this function here. Let's do this. Let's call this vector vel is equal to a s, or current velocity or previous velocity multiplied by s plus 0.5, or I should start with the vector. So the previous acceleration plus a new acceleration value, which I've already calculated, which is this one, which is this right here, and we use the parenthesis and multiply by 0.5, multiply by dt. dt is the time step in this case. So we also need to have a time step value. Right. Now I might need to apply the time step to the acceleration as well. I haven't done it. Maybe I should. Let's think about it later. Okay, so I have dt, and let's call the time step 0.01 for now. And I have this value. Next thing I would like to do is so now that I have calculated this velocity, it's time to clamp the size of this velocity with this displacement value. So in order to clamp it with the minimize function, what I'm going to do is to first of all normalize the velocity, then get the size of the velocity and use the minimum function with this d divided by dt delta t. Alright, that should do it. Okay, and then now that I have a new velocity, I can now update the velocity with this new one, and also update the acceleration with the new acceleration value. Right, that's just that. Okay, so now I have updated two information, velocity and the acceleration. It's time to update the point position as well. Going back to the previous node, just need to do the similar calculation right here. So in order to update the point position, we have the current point position, and using the current velocity and the current acceleration, multiply by the delta t, and clamp it with this displacement value. So use the same displacement value. I'm going to create another d value here as a parameter. And I am just going to copy or link what it has here to this one. So we are going to use the same value. Okay, other than that, we can just try to calculate. So just going to try to create a function called a vector called new pos, which is, wait a minute, maybe first of all let's calculate this part first. Okay, so let's call that add position, which is a current velocity multiplied by dt. So obviously we need to have a delta t time step value as well here. Let's link that as well. Copy this delta t to this one, and then plus a current acceleration multiplied by 0.5 multiplied by dt by dt. Okay, So this is this equations right here. Now we need to clamp the size using the minimum function, just like we did for the velocity. So add pos is equal to, first of all, normalize the position and multiply by the length of add pos, and use the minimum function to clamp or reduce the size using d. That's just that. Oops. Okay. And then finally we can add it with the current point position to create the new point position. So new positions is equal to the current point position plus the add position. And we can now update the current point position with this new position. Alright, so that should do all the job. And let's see what it's going to create. And now, right now, I'm brute forcing, or I'm just retrieving, trying to calculate distance between all the other points, so it's going to be really slow to calculate. But let's see if it's still going to work or not. Right, so let's check. If I play it, okay, obviously the simulation is slow and I am seeing some caches, so let me start from now. As you can see, I can now see the point has been normalized in terms of this distance, and I see one problem is that it's inflating and it's not really clamped in the boundary. So we need to think about how we deal with the boundary as well in this case. But if I look at the effect, it seems to work as it's supposed to, although it looks a bit too slow. Okay, so at least for the first try it looks good. Now let's try to fix the boundary issue first of all, and let's see if we have any information about that. And yeah, I think it explained about it somewhere, forgot what. I think it's if you search it with a periodic or something. Okay, so the process is simulated in a periodic domain, meaning if one passes the boundary, then the point will come from the other side. So if this is the boundary, and if the point goes beyond the boundary, let's say the point goes underneath this boundary edge, then the point will come back from this edge and go to the bottom direction. If the point goes to the right directions and go off the boundary, then comes back from the left side to go to the right direction. And that's what it means by this periodic domain, I think. I assume. So let's try to do that. It's not that hard to implement. You just need to move the point once the point passes the boundary. So let's give a simple boundary functions as a point wrangle. And let's see. I'm also going to give a little bit of offset. Like I'm going to create a little offset maybe outside the boundary when the point should goes from one side to the other. Because if I try to use the very boundary edge right here to move the point, it might give a little bit of flickering around the edges. So in order to avoid that kind of flickering stuff, I'm going to create a little bit of offset for the boundary. Right, so let's give some float value. Call offset. A very small number is fine, I think. Let's say like 0.05 or something. And then since I know that the size of this plane is equal to 1 for both width and height, so it's easy to think how the boundary should work. I'm just gonna call the size as 1, call it as S. Now if the point position dot x is minus offset, then move the point to the right side by adding s plus offset multiplied by 2. So if the point goes to the left side, and let's say the boundary is somewhere around here with the offset 0.05, then move the point back to the right side by moving the whole size plus offset multiplied by 2, so the point should appear somewhere around here. Okay, that's what it's doing. And do the same for the when the point goes from right to left, point from bottom to top, and so on. So we need 4 conditions. Just gonna copy 4 times, and if the x goes to the right side, which in this case a 1 plus or s plus offset, then you wanna subtract by s plus offset by 2 multiplied by 2. Okay, now if we also would like to think about the z direction, maybe I can just copy these part and replace with the z, and that's all we need to do. Just like that. Right? I think it's gonna work. Let's see. Now let's redo the simulations, and hopefully the point wouldn't go outside the boundary anymore. As I said, you do see a little bit of flickering near the border, so that's why I had set this offset value so that we can clump around the boundary. So right after we have leave the solver, I can then use another point wrangle to trim out the points. If the point dot x is larger than, let's say the size is equal to 1 as again, and if x is more than s, or at p dot x is less than 0, or at p dot z is larger than s, or at p dot z is less than 0, then we can just delete those points. And do we see the trimming? Yup. But I still see some caches. Okay, this happens. Okay, let me reopen the file. Okay, now the border has been trimmed by the offset, and you should be able to see a bit more cleaner image of these point distribution. Now that's fine, and the only problem left is the speed. The calculation speed is slow, obviously, because we are calculating the n multiplied by n, brute forcefully calculating, and I'm not doing any optimization for the GPU, obviously. Just did the brute force calculations here, so In order to make it faster, I'm going to update the function for the acceleration a little bit right here to make it a bit more faster. Okay. One thing I would like to test out. Let me move those value to the somewhere around here. Well, I just want to check what happens if I multiply dt to this new acceleration value. Guess it's doesn't really change the result. No, it's too slow to check, so I'm just going to leave this without it. I'm gonna check this later. Remind me if you could remember. Alright, so in order to make it faster, maybe I can keep this for reference. And to make it faster, I'm going to use a other function. Rather than looking at all the points, I'm going to reduce the number of points to do the sampling. Okay, for a faster result. And because of it's going to reduce the sampling points, the result might not be accurate as the original solution. But I mean, I just wanted to test out. So in terms of the visual, it doesn't look that bad. So for my case, it's still fine. Alright, so first thing first, where I can change, I can go back to where I have calculated this fi here. And this is the problem. This is where it makes all the calculations so slow because we're sampling all the other points. So if we could reduce the number of points to sample, then obviously we could reduce the speed. I mean, we could speed up the process as well. So what I'm gonna use is to search for the nearest points, number of nearest points from point I, or at P, position I. So if the position is close enough, if we are looking at this point, then we're only going to sample those points within some range, or limit the total number of points to sample. So that's what I would like to do, and the function that I'm going to use for that is new points. So let's use this, and pts is equal to near points, and the near points can get a number of points based on the search positions by setting up the search radius, as well as the total number of points, the maximum number of points to use. Okay, so we're gonna set both of them, or maybe setting the maximum number of points is a bit more easier to control the speed, because if we have tons of points in a dense plane, then even if we have reduced the radius, there's a chance that you still get like tons of points, and still going to make the calculation a bit too slow. So I am going to mostly focus on this parameter, int max pts, reduce the total number of points to sample. In this case, more points you sample, more accurate result you get, but less point numbers, you get faster result. Okay, so let's see the difference. So 0 at P, and for the search radius, we can just say really high number, like 1000 or 100. Since the plane size is 1, maybe even 10 is fine. Then we have this point, maximum point number, which I'm going to make it as a parameter. Okay, so starting with maybe 1000 points. And now in maximum you get 1000 points from each point. Okay, so I just want to replace these part with this new point list. So I'm gonna replace this with NPTS, length of NPTS, and I guess I should change the iterations to something like n as well, because I want to use j as a point number. Okay, and if I is not wait a minute, this is all okay with j. Now, oops. What I want to do here is to get the point number j from the NPTS by accessing to n index. Okay. So all the following code is kept the same. What I just changed is these part. And for the other one, I think you can just use it as it is. And let's see the result. I'm gonna replace it, this one, and see what happens. Now you still get the similar result. I don't know if it gets faster. Not so much. Let me reduce the number to 100 then. See if I can reduce the speed. I mean reduce faster in the speed. Now obviously it becomes more faster. Okay, the result become faster than before. Okay, so maybe the number 100 might be a good idea to test out for a faster result, and the result is not that bad, I think. And let's try with more point numbers. Let's say 50,000. And still the speed is not that bad. Maybe it's the only problem I can see is that it's hard to converge if you have a small number to sample. You see that the point is keep moving. One of the reason is because at each frame the point is like moving back and forth, even though it is at the converging state. So the one of the good idea to not move the point when it has been converged and keep the substep equal to 2, so that you can, if it's converged, then the point should stop at some point. Now if I look at it, some of the point is still moving, and maybe in this case the d value might be too big for displacement. I mean, I think if you just sample all the points, then it just converge in a really stable state. But obviously you can see that the calculation become a lot slower if you increase the sample numbers. So I guess that's the reason why you want to use GPU for the accurate and fast implementation. This is just a fast and dirty implementation that I did using Houdini, just because I wanted to try out. So, but in order to understand how it works in terms of the algorithm, it's quite enough for me, and it's pretty interesting. Now it's a bit hard to see if it's been converged, so I'm gonna keep this to 100 and try to reduce the d value like 0.0015. Since I have so many points, the displacement can be smaller, I guess. Still moving, but not that bad a result, I guess. And I could also try to multiply this dt that I forgot to test out and see what happens. Maybe that doesn't really give any. Maybe that doesn't really do anything, so forget about it. Alright, but after all, I mean, I can see that it is creating a blue noise sampling, the sample blue noise. So the initial goal in order to create a uniform sampling is done with these, and using this rather dirty way to implement to make it faster, it's still kind of a work. So let's say it's okay. Alright, so let's reduce the number of points to 10,000 again. Yeah, this one seems more converged. Okay, not bad for result. Alright, now that I have done a step 1, it's time to go to the step 2 to use the image, the actual image for the adaptive sampling. Now in order to do that, we need to calculate this G value as a negative. I mean, this KQ as a negative charge value. Then calculate the new acceleration value for the particle. And this total amount of negative charge and the total amount of positive charge should be equal to the addition of those those positive and negative charge should be equal to 0. And that's where, by doing that, you'll be able to get the finalized vector value in order to move the point at the right direction for the convergence state. Right, so let's do this, shall we? And before doing that, I'm going to move all those parameters that I have set, like ds, dt, to the controller. So I'm gonna open up the parameter editor, going back to the solver, drag and drop the s value, d value, dt value, max pt num. Okay, let's make everything lowercase. This is okay with the capitals. Okay, and let's also link with this one as well. So I'm gonna copy, paste it right here. Paste it right here. Wait a minute. This is the dt. And we're going to copy d, which comes to this. Okay. And it might be a good idea that if we give an option to switch between the brute force way and the dirty and faster way. Let's give a toggle to switch between the fast mode or the slower mode. Going back, copy the fast mode. Obviously for the movie stippling or video stippling, I'm gonna use this fast mode because I cannot wait until all the convergence is done for the slower implementation for this one. For if you want to use the full implementation, the accurate implementation, you just need to use GPU or OpenCL, I guess. Alright, that's a reminder, and let's do the adaptive sampling then. Alright, So everything is quite close. First of all, let's calculate this QK by the intensity of the image together with this A value. And as I said, A is the coefficient value which is determined by the total amount of the positive charge. So the total amount of this positive charge and the total amount of negative charge, the sum of these two values should be equal to 0. So we can assume how much the A should be by those equations. Alright, so let's do this, and we can do this inside the stippling node. So let's do this. Maybe we can do this in the slower. Yeah, I'll just do it faster and move it back to the slower later. So we're going, in this case, we're going to calculate additional acceleration value called GI. Previously we have calculated FI here. So let's say this is for the uniform. And this is for the adaptive. Okay. Now, first thing first, we need to calculate this QK. K, and which comes from I, and we don't know A yet, so let's just have these values first. So the intensity is, do we have that? The intensity value is applied in this plane right here, which is this cat image. So we're gonna use this as a reference for the solver. So gonna connect this to the second input to the solver, and we need to check that if the image is overlaying with the scattered point, and right now it is, so we can just use this. Now if we look at these equations here, right here and right here, IK is the intensity of each pixels in the grid of this image. And we can get that by accessing to the, which one? The CD value, or we don't have that yet. So let's give a float IK, or let's just say I. Float I is equal to a hsv.z. Okay. So we have this intensity value from 0 to 1. If it's equal to 1, then we have white value. If it's equal to 0, we have black value. So more white you have, you get 0 with these equations. So you have more negative value, meaning repel force. If it's close to 0, meaning if it's close to black color, you get a higher negative value. So meaning you have strong cohesion force in this case, I think. So you have more point density to where the intensity is close to black or 0. And if it's close to white, meaning close to 1, then you have more separation. So less point density to those areas. That's what I assume. And let's see. And for those information, this is the point, the current point position of the scatter point, which comes from this one. And RK is the point position on a grid, on each point position on a grid. So if you show up the edges, these are the points that we're talking about. Each point is considered as a single point on a grid, which every point has an intensity, which is called as K. So in this case, we have more loops than the previous uniform sampling. We have, in this case, 262,000 points, and obviously if we try to calculate the loop for all those points for each Ri, then that's just too much as again if you want to do it in CPU. So we're going to reduce the number of points to sample again for this adaptive sampling. So that's kind of a, I don't know, maybe I can call it a fake or really dirty way to implement to make it faster, but still seems to work in some level, so just gonna try to do it that way. Okay, all the other things is similar to what we have done in Fi, like we have a unit vector value from k to I. We have qk, which I have calculated here. We also use the qs that we have been using in right here as well. So let's do this. Let's do this, shall we? Going back to the solver, and let's first calculate this one. So float qk. So let's ignore a for now. So negative 1.0 minus I, and in order to get intensity value, we need to access the grid information. Now, maybe the qk is defined for each pixels in the grid, so maybe I don't really need to do it inside the solver. Maybe I can just do it outside when we have calculated the intensity right here. We can just calculate this part at least. So let's say temporal qk, or temporal qk is equal to 1 minus I, or just say hsv.z, so we don't really need these one. Okay, and let's create the comment 1 minus ik. So this is just a comment to indicate which part I'm referring to inside a paper. Okay, so this is the temporal qk, which is just this part without the a value. Maybe I can also make it negative. Like this. Okay, now going back to the solver. The first thing I need to do here is to calculate this a value. And in order to calculate this a value, you need to first calculate the total qs value, the positive value for each point, for each scattered point. In this case, if we go back to where we have calculated this fi, I am only sampling a number of points, in this case 100 points by this parameter. So meaning I have 100 positive charged point for this calculation. Okay, and each of them are using the same qs value, so meaning the total charge of this the total charge value for this point, the specific point, is equal to a maximum point number multiplied by qs. Okay, so that's pretty easy to calculate. Float total qs is equal to a maximum pt num multiplied by the qs. Now since I am using the new points, and new points also includes the point itself, meaning I, there always is a I value within this NPTS. So I think it's a good idea to subtract this maximum number by 1, so that this is the actual charge number, the point number that is actually used as a calculation within this condition right here. So if the maximum point number is 100, then the actual point number to calculate is 99. So 99 multiplied by Q is the actual total positive charge value. Okay, and in order to get this A value, the calculation looks like this. So total QS and total QK is equal to 0. And in order to calculate this total QK, we need to define how many points we're going to sample from the grid image. So that's what we're going to do next. We don't know yet how many points we're going to get, so we're going to do the similar things that I did using this function near points. So let's keep this for a while and go to the next step. In order to sample all the points we're going to use for the negative charge or adaptive sampling. So and PTS. Maybe I should rename this. How do I name this? APTS, I guess, is equal to near points from, and in this case we're going to search from the second input, meaning I'm going to connect the grid image to the second input. Then this grid image is what I'm going to refer to, which is the cat image. Okay, and I'm going to get those necessary information like intensity value to calculate the QK and so on. So from the current point position, search from the current point positions, and maybe set the maximum distance, maximum search radius with the big number, and then use the same maximum point number. Maybe I can just create as a variable. Maybe you could also use the different number of point number for a adaptive sampling. But for easy testing, I'm just gonna use the same value. But you can, I think you can also change the number of point to sample for the uniform sampling and the adaptive sampling if you want to see the result differences in terms of the quality. Okay, I'm going to replace with the variable. How's that? Right, so where were we? Now I'm going to get all the sampled value. Like this, and then so I'm using the same maximum number, in this case 100, so probably I'm getting the same 100 numbers out of this APTS. Okay, now let's do the loop. Just gonna copy all these for ease. Let's give a little bit of space so that it's easy to see. Okay, so I'm gonna replace some of the variables. So looking at all the APTS and the J, in this case we are naming K, so let's name this K. Integer K is equal to APTS and index. Then if I is, now there are no chance that I becomes equal to K, so we can remove these conditions because we're looking at the different input. Alright, like this. And after we have got this K value, which is the point number, we can now try to get this intensity value right here. I mean, I've already calculated this minus 1 minus ik. So let's get that, which was called temporal qk, right? So float temporal qk is equal to a point from second input. The name is equal to temporal qk at k. All right. Now that I have got these one, what I can do now is to try to get the total amount of qk right here. So float total qk starting from 0, and each loop we can add this temporal qk to this one. Maybe I can call this temporal tqk, total temporal qk. It's a bit confusing. All right. Now for the other part, we could just try to calculate the one without this qk part. So let's do this. Or maybe we can also use the temporal qk instead of the actual qk. We can just, the a always becomes a constant for this specific point, so we can just multiply it later for this a. So let's forget about this one, but let's try to do these one first. All right. So so position I is okay. Position k, we can get the position k from the second input with the number k. Right, and what we're going to have, what we're going to calculate is the, first of all, unit vector from k to I. So this becomes k, and then divided by this, the lengths between Ri and Rk, and squared. So position I, position k, lengths 2, right, and finally we can multiply it by this qk. In this case, I can just try to multiply with the tqk for now without the a, value, because we don't know this value yet. Alright, so, and we can add that to gi, and we don't have this gi yet, so let's create a vector starting from 0, 0, 0 as a gi. Okay, and after that, after we leave the loop, we do the same things as we did for the fy, multiply with the square of qs, so like this one, gi multiply by qs and qs. Okay. Now with this calculation, we have mainly calculated two things. One is this gi, which is still missing this a value, and well, I also have calculated this total temporal qk, which is the total addition of this 1 minus ik, the negative 1 minus ik. Okay, so going back to sketch, we can now estimate what a is by all those information that I have. Now, all the positive charge has already been calculated as a total qs. Okay, and this is a positive value. And currently, at each loop, I have calculated minus 1.0 minus ik using a loop. Okay, so, and calculated as total tqk. Okay, and the solution is that in order to calculate the A value, total QS plus total TQK multiplied by A should be equal to 0. So A in this case will become minus total QS divided by total TQK. And as a result, you'll be able to get this A value, and then finally you'll be able to get this GI value by multiplying this A to this temporal GI to complete this equation. Okay, sounds confusing, but this should work. Alright, so let's do this. What was the equation? So in order to calculate this A, we are going to divide the total QS and total TQ at K. Okay, I have named it, too bad. Let's do this, shall we? So A is equal to minus total QS divided by total TQK, right? And finally, we can multiply A to this GI, and you should be able to get the result. Hopefully. Right? And let's see if this is really going to work. Alright, so now that I have GI, I can go back to where I have calculated this new ACC, and this is pretty easy. You just need to add GI as an additional force. And I think that's pretty much it. And let's see if this is going to work. Okay, finger crossed, and there you go. The convergence seems a bit too slow. Maybe the D value is a bit too small here. Maybe not. Or the number of points is not enough. Not sure. Maybe I'm missing something. If I increase the QS, maybe I was just seeing the cache. Maybe that's the reason. Okay, the result looks not that bad, even though I'm just sampling closest 100 points. It still gives you a grasp of cat. Maybe I can increase the point radius a bit. Okay, and maybe I can try to increase the point number as well a little bit. Maybe the radius is a bit too high. And there you go. I can clearly see that it really looks like a cat. Alright. Now it still is not that fast if we have like 50,000 points, but it converges it pretty fast. I do see a little bit of flickering because of the the less sampling values and maybe a bit too big displacement. I'm not sure. Maybe not. Maybe this is the only reason why it makes a bit flickered. Okay, but seems like it gives a good result, a rather good result. Not bad at all, I guess. All right. So, so it seems to work in a static image. It's now time to test it in a sequence of images and how it affects. And because this is based on the physics-based simulations, meaning we're just moving the point based on the charges, it really works well in the animation. All right. So if the animation we're going to use is a smooth animation, then this should work pretty fine. Let's reduce the number to 30,000. Now this seems to converge the point positions a bit better in terms of those single colored part. And we could also play around with this QS and maybe the D value. If I make it 0015, the point no longer moves that much because we are reducing the point displacement distance, but then some of the point is missing to go to the right positions. It just stops at some point, so makes a bit more blurry result. Maybe that's not really what we want, so maybe keeping this to 0.002 is still a good idea. Is it I have a comment. Is it possible to use in this type of calculations OpenCL, and is it implementation Vex? Yeah, it is totally possible to do it as an OpenCL, and I think the paper is also intended to use it inside OpenGL, I mean the GPU. So obviously it can also be used in OpenCL as well, and for sure it's going to be much faster in OpenCL. So if you know how to write it on OpenCL, I would just recommend it doing that instead of Vex, I think. As I said, this is a really dirty implementation just because I wanted to make it faster inside Vex, and I want to test inside Vex. But really not really necessary to do in Vex, but can directly port it into OpenCL for sure. Okay, so let's test this out in a sequence of video. Sequence image from the video. I'm gonna use is the one that I've downloaded from Envato. Yes, this is the water drop image. Any image should be fine, I think, but this one has a like strong contrast between white and black, so maybe I thought it would be a good testing image. So let's do this. So in order to use this inside Houdini, we need to convert this into a sequence of images. So, and I guess there are tons of ways to convert this into a sequence. What I'm gonna do is to use a FFmpeg to extract the images from this MP4. So in order to do that, first of all, I'm going to go to this directory. Then there should be a command in fmpeg to extract the image. Let me search for it in Google. So there's this. I guess I can use this command, fmpeg -i name of the movie, the name of the sequential frame image. Alright, let's use this one. So the name of the movie is this one. So FM MPEG I water drop MP4. Okay, forgot the double quotation. Not sure if I need it. And the output names, let's create a frames folder. I might need to create an empty frames folder. Oops. So frames out 03d.jpg. Okay, so how's that? Alright, so it's now extracted the video into the sequence images, and in total I have 277 from 1. Okay, so let's read those information, read those textures. Now let's forget about the aspect ratio of the image. I'm just gonna make scale it to a square because it's time consuming to just trim it out. So going back to the attribute map, looking at the image right here, let me duplicate this one, and first of all I'm going to refer to the single frame image and replace this with the frame based value, so which can be done by using the function called pad0 / and use the pad0 function. The size is 3 and we're gonna convert frame. So 1 becomes 001, 2 becomes 002, 13 becomes 013, and so on. Okay, let's check it. Alright, now I can get all those images. It's until 277. Alright, so now it's time to actually see how the point changes based on this frame sequences, if I need to do any extra things. I'll play it. Wait a minute, I might need to look for the no. Let's test this out. I do see a little bit of ripple here somehow. Maybe there are small like contrast differences in the actual image. Now, if I look at closely, the point is somewhat moving following the underlying image. Let's play from right here. Okay, and it doesn't look that bad. Maybe I can control the contrast of the image a little bit for those underlying like ripple like image, but the result looks quite good. Now these part is not converging that much. I guess that's because of the contrast that I was saying. So let me go back and tweak the intensity value a little bit to clamp the maximum than the minimum. A little bit, just a little bit. So everything looks white, but if I look at the actual color, as I see, some of the value is not really clumped to 1, like these. So those differences are making a little ripple effect, I guess. Maybe if I could be able to sample all the points rather than just getting the closest 100 points, maybe I'm getting more converged nice state. But that's too slow for my dirty implementation, so in order to reduce that, I'm going to clump the contrast a little bit by using the f at tk, or I'm gonna get the intensity float I is equal to clamp the hsv.z by the minimum and the maximum. Then convert it back, or remap back to 0, 1. Or I can just use the fit as it is. Yeah, I guess that's faster rather than using clamp. Okay, so fit like this. This should be faster. And I don't really care about the black part, but let's make the maximum to 0.95 so that the white part will be clamped. And let's look at the and I'm going to replace this with I and see the result. And everything is 0. Maybe I'm doing something wrong. Alright, so I have... Wait, that's correct. Yeah, because I'm subtracting 1 by 1, so I think that's correct. Okay, let's see what's gonna happen. Okay, so it looks more uniformed, and the result looks more crisp and contrast with a little more contrast. It still is not that fast, even though I'm just sampling 100 points, but not too bad, and the result looks also good enough. Yeah. Okay, let's wait for a while. Let's do some caching until the last and see how it's going to look like with the smooth animation. Gonna make a cache. And while doing it, maybe you can try out with the other types of images. Or video. Like this one. What spec CPU are you running on this? Oh well, I'm using a M1 Mac Mini, so not that fast, obviously. Alright, so this is the result. And this is what we get out of this simulation. Not bad. It's kind of taking time. Maybe I'm because of this caches. If I keep opening this Houdini, it happens a lot with my Mac. Let me reopen it. Okay, but the result looks pretty nice. Pretty nice. Alright. And so I assume the way I implement it is not too far away from the original solution. I mean, I am skipping a lot of stuff, the important optimization stuff for a GPU, but at least seems to work in terms of the visuals. And I know what's the limitation for my implementation, for my dirty implementation. So, and you should also know that, since I've been keep saying it. So if you want to have the full implementation, the full result, full accurate result, then you should go back to the paper and then use it with the GPU or OpenCL or something, Perl based processing rather than using CPU. Okay, but so far so good. Let's try it out with this doggy image that I've downloaded. See if it's going to work as well. Let's replace this. And there you go. It's kind of a squeezed, so this became like another type of dog, but still look like a dog. Okay. Maybe because I'm reducing the number of sampling, that's the reason maybe I'm having this kind of a white space on outline. If you look from the far away, maybe that's not that obvious. Maybe that's obvious. I'm not sure. Okay, but so far, so good. Just wanted to test how it works and pretty satisfied from what I get. Let me know how you think. Let me know if you have any idea how you can make this more efficient, more faster. If you maybe I would like to try it with OpenCL implementation as well later. That's one thing that I need to try out for this setup. For a GPU, I guess you need to go for shaders and so on. But because if you use shaders, then you no longer have an access to those point to information as a geometry, so that might be a downside for it, because you do want to access to those geometrical informations if you're using Houdini, because you can apply all the other attributes as well to those points, so you have much more like possibilities using those, addition to those stippling. Right, so that's about it. And if you have any comment or questions, let me know. What I've done here is just trying to follow what it explained in this paper, so I can't really tell why this works in a specific way, but it looks pretty straightforward. This Fi is creating a repel forces to keep the distance for each point at the same distance using the maximum displacement value, and Gi is controlling the cohesion forces by changing the attraction amount based on the sampled image using the intensity. The key point of this calculation is to keep the total amount of the positive charge and the total amount of negative charge be equal to 0, and I think that's the most important part. You should keep in mind, because previously I forgot thinking about it, and previously I tried setting this a value like as a constant value for all the points, and it didn't really work. It just gave you a really blurred image, and I thought that was the correct image. But as soon as I changed the equations to so that the positive and charged value became 0 in total, then the image became more crisp. So that's the key of this equations, I think. Hope it makes sense. And if you're done with these informations, then I think you can obviously create this 2.5D image stippling together with this depth image pretty easily. You just need to update the adaptive GI sampling force with additional like epsilon value, or should I call this epsilon value, which is does it explains. I didn't really read this far. So epsilon maintains the minimum distance between particle. No, this is where does it say? To achieve this review, displace the whole density field toward the sampling plane. So the depth field is used to control the focus distance, I guess. So if you want to make it focused, then you can, I guess my guess is that keep the distance between the original imaginative plane and the underlying image plane the same. Now, if you want to make it blurred out, then you can change the height, or you can change the position of this plane in terms of the z direction. I mean the y direction. So, meaning in this case, by just moving this image upward, you can make the distance far away from the original plane. Makes the whole image a bit blurred out, I think. Let's try that out. If I make it, translate it. Maybe that's too much. If I make it 0.2 or 0.25 and use it to calculate the distance, then something might changes. Let's see how it changes. Now everything seems blurred out. Maybe that's too strong. Let's keep the distance a bit slightly upward, 0.05. Now I can see a little bit of silhouette, and compared to the last view, it does seem I blurred out and you have more contrast on those chair part. Interesting. And I guess using a height field means is that to control the height for each point. So closer the distances, you have more crisp image. Farther the distances, you have more blurred image. That's what I assume. I didn't really try it, so. Interesting. Alright, you could test it out yet. Test that out for yourself. Okay, having a little bit of distance makes a bit smoother result, I guess. So maybe translate a little bit upward might give you a little better result. Not sure. Maybe a little bit more. I really gotta play around with these parameters to see what works in what way. All those assumptions are just my assumptions, so it's not really. I'm not really sure if that's that. And if I increase this d value, maybe, yeah, I have more convergence. Oh, looks better. Alright. Oh well. I hope you find something new here. I did learn new things by implementing this one, and all the credit goes to Kin-Ming Wong and Tien-Tsin Wong for sure. This is really a really exciting paper to look at, and it was pretty interesting. I really enjoyed implementing this for myself. Okay, and I hope you did as well. Okay, so after this live, I am going to upload what I have done to a GitHub as always, so that anybody can download the file for your reference, to look for your reference. And play around with yourself, and maybe convert it into an OpenCL version. If you do that, let me know, or give a pull request on GitHub, then that'll be great. Okay, so that's it. Any questions? And there I have a comment. This reminds me a little bit of the way to extract 3D mesh from several images with different depths of field. Ah, that's true. It's interesting. Think it's using a forgot what it says. A surface. It's called a surface reconstruction. No, from several images with different depths of field. I'm not sure how I code, but maybe that might be a similar things. I'm not sure. Not sure. Okay, so if you don't have any comments, I would like to end the live stream here. Thank you everybody for watching, and thank you for all the comments. Maybe this was too mathematic for today. Hopefully you find it interesting in some way. I do kind of enjoy this kind of paper implementation myself. Hope you do as well. But I guess it's only fun when you actually read the paper by yourself and implementing the equations by yourself. So I think it's I think it's better if you try implementing by yourself. First of all, without looking at the file, then come back to the file to see the differences from what I have implemented and what you have implemented from the same paper. Maybe the method might be different from mine and yours. That's also interesting. All right, so thank you very much. Hopefully, what's happening here? Is this correct? Let me try without the QS. Interesting. Maybe I can parameterize this value as well in terms of the height. So let's give a image height from 0 to 1. Maybe 1 might be too big, but like this. And these one we can switch between the images. Just like that. Okay, any other parameters that I forgot to promote? Oops, forgot to set the boundary. And I think I got every parameter set. Okay, that looks good. And if I change the height a little bit, interestingly, it converges faster. Oh, interesting. Nice. All right. A comment for me, the hard part is have little bit of knowledge how to properly read the equations. That's true. That is true. I mean, in some paper the equations written in different formats, so it always is a hard part to to understand, to properly read a paper. It is hard. It is always a hard part. I always get lost reading those equations, and in this case this was pretty straightforward, so that was good. But in some cases I do get lost a lot. So, but this paper is pretty straightforward and well explained. It's really a good one. Okay, thank you all, and hopefully enjoyed. So as I said, after the streaming, I am going to paste the URL to this file for the download, for you to download in the video description page of this live stream on YouTube. And also I'm also doing the Patreon, so if you're interested in supporting me, I appreciate that as well. Okay, that's it. Thank you all for watching, and good night. As soon as I finish the live, I'm gonna post this file. One thing to mention, I am not going to include the image file that I've downloaded because that is copyright protected. So for the image to use, you just need to download yourself what you want to use. Okay, that's just that. Alright, so that's it. Thank you, and good night.